Good morning, good afternoon, or good evening, wherever you are joining from around the globe. I'm Aklilu Abrham, assistant professor, academic researcher, and data analyst. Have you ever wondered why so many promising students fail their thesis or dissertation defense? Or why brilliant manuscripts keep getting rejected from reputable journals? One overlooked but critical reason is ignoring the importance of checking for data normality. Here is what happens. Students often dive directly into analysis, assuming their data is normally distributed, and later discover the results and the conclusions are incorrect. This oversight frequently leads to tough examiner questions, extensive corrections, or worse, complete rejection of their thesis or dissertation. Manuscripts submitted without proper normality checks typically face rejection from journals because peer reviewers quickly spot inappropriate test selections, flagging the research as unreliable or invalid. But don't worry, today I'm here to save your thesis, dissertation, or manuscript from that fate. In this step-by-step video, you'll learn why normality assumption checking is essential for deciding between parametric and non-parametric tests, common errors students and researchers make, and exactly how to fix them, clear strategies to visually and statistically assess normality, such as QQ plots, skewness, kurtosis, histogram, and others, and also how proper normality checks save your time, energy, and countless revisions. Watch till the very end because I will reveal the single best solutions, and also I will show you single biggest mistakes students and researchers make. This one oversight is responsible for numerous test rejections and manuscript failures. Trust me, you do not want to miss this crucial step. This is the dataset I have used last time in video 1. We get this dataset from Kaggle, and if you are new to the video, please watch that video and get this dataset. Or you can open your dataset and you can move together. So to check the normality, let's click on Analyze, then Descriptives. From the Descriptives, click on Explore. When you click the Explore, you will see this window. So let's bring our dependent variables to the dependent list. Here it is. And let me bring ID, level cases by ID. I want to level case by ID. You can put it empty, no problem. But with ID, it will be more clearer. In the factor list, you can put factor variables if you are interested in. For example, you can compare between male and female, or you can compare between those who use social media and not use social media, like that. If you're interested, for now, I will keep it blank. Let's click on statistics. In the statistics, it will provide me descriptive statistics here with 95% confidence interval of the mean. And there are also others, but let's check also outliers. But usually descriptives might be enough from here. In the plots box, I will select histogram. I don't want stem and leaf. You can tick histogram. And other important part is normality plots with tests that will provide us Kolmogorov-Smirnov and Shapiro Wilk test. That's good. And in the options, I will keep exclude cases listwise to compare listwise. The other, yeah, I don't want to check on Bootstrap. The display option, I want to see both statistics as well as plot. So I'll keep it like both. Then click OK. That's running. Okay. Now here it is. So here each size the function was explore. So we have checked this in the explore. I think you remember that. Descriptive statistics explore. So that shows the other case processing, our sample size and missing values. So in our dataset, there is no missing value. So all of the sample size, all of the participants respond to the question. So no missing value. The descriptives part, our first dependent variable is ADHD. So here there is a mean value of 12.81 with standard error of 0.173, and for the mean value there is 95% confidence interval. That means in the dataset 95% of the ADHD values will fall between 12.47 and 13.95. That means there is 5% chance that the mean value will be outside of this box. The other important result here is 5% trimmed mean. That means SPSS trims or removes 5% from the top and the bottom. That means the highest and the lowest values, the 5% will be removed, and then takes the mean value of the rest. So look, the 5% trimmed mean is 12.87 and the whole dataset mean is 12.81. The importance of this is if there is outliers in either direction, in the lower as well as in the upper part. So if 5% removes the outliers, and if when 5% removal creates a huge gap in the data, in the mean values, if you detect that, so it shows there is an outlier there in your dataset. So you have to go there and check and correct that. Let me show you this by an example. Let's go to our dataset. Let's make, for example, this is the first one. It's 15 normally. Let's make 2 zeros, 1500, and rerun the explore function. Here it is. The mean value is 15.90, but 5% trimmed. Mean value is 12.87. That means the 5% trimmed value trims the outliers. So the mean, this trimmed mean, is much more describes the data rather than this one. So this shows this mean will be affected by the outlier. So for the researchers, students usually check the closeness of the mean and 5% trimmed mean, and also the median. If they are closely related, if the numbers are very close, it's a sign of normally distributed data. let me correct this one and save. So that's important. So as a researcher, we always check the mean, 5% trimmed mean, and the median values. If these are closely, if the numbers are very close, that shows a good sign of normal distribution. And yeah, we'll check further, but still, it has some hints. But if the mean and 5% trim mean, the value are very far away, like for example, the mean is 20 and the trim mean is 12, it shows there is an outliers in the data. So that should be handled. The other important part here is skewness and kurtosis. Especially skewness tells about the symmetry of the data distribution. In the normal distribution, the data is distributed bell shape, and in case of positive or negative skewness on the skewed data, this bell shape might be distorted. Data may be, for example, negatively skewed. In case of negative skewness, negatively skewed means most of the participants have larger or higher values, and few of the participants has lower values. Let me say that by an example. For example, in a classroom, when a teacher examines the student, if majority of the students pass the exam, it means let's say score 90, 95, 100, and if few students fail in the exam, this indicates that the data are negatively skewed. That means majority of the students have the high score, and the tail is long towards the negative the long tail towards the negative end, to the lower end. The reverse is true. If the data is positively skewed, majority of the students fail the exam. The exam may be difficult, but few students may score the highest score. Few students. It means those outliers pull the mean. So checking this skewness is very important. For skewed data, researchers advise to use non-parametric tests rather than parametric tests. The acceptable range usually is in many books you can find -1 to 1 is acceptable. In some books, to confidently accept -0.5 to +0.5 is acceptable. Whatever, if it is closer to 0, both skewness and kurtosis, that's good. That's good. Kurtosis about how steep the data is, the shape. If it is positive, the graph will be peaked. The data are closer to the center, and if it's negative, it will be flat. It will be flatter and flatter. So we will check that. So from this, let's decide about our data. The mean and 5% trim mean are very close, as well as the median. So this indicates the data satisfies one of the normality assumptions. The other, kurtosis and skewness. By the way, there is also one tip. If the sample size is large enough, that means if the sample size is greater than 200, you should not worry about the skewness and the kurtosis, says some literatures. So in our case, sample size is 481, so skewness may not be a concern, but normally it's also still it's closer to zero. It's closer to zero. So both of them are in acceptable range for ADHD. Let's see also for anxiety. The mean and 5.5% trim mean, they are also very close, 6.80 and 6.89. That's good, and the median is also 7. So still this is in the acceptable range. The same is true for skewness and kurtosis. About self-esteem, let's see. About self-esteem, the mean is 8.06, 5% trimmed mean 8.01. So still it's very close, and the median is 8. So that's good. And skewness and kurtosis, they are also very nice. And for depression, the mean 9.63 and median 9.69. That's good. And also the skewness and the kurtosis. So all of them satisfies the assumptions. So one of the assumptions is descriptives. The mean, median, and the 5% means are closely aligned. aligned. So it passes that. The other, here is the extreme values. The largest 5 and the smallest or lowest 5 values are listed. In our case for ADHD, the highest values are 20. These are the IDs. ID number 15, 35, 52, 67, and 72 has 20 in ADHD total. So it shows the highest and the lowest. You can check. But just means extreme values are not outliers. It just only shows the highest and the 5 highest and the 5 lowest values. To detect outliers, box plot is much better than this. So let's see tests of normality. That's another important test to decide or to check test of normality. Here there are Kolmogorov-Smirnov and Shapiro Wilk tests are provided. For both of them, the test statistics, degree of freedom, and significance or p-values are given. Shapiro Wilk's test is really powerful in smaller sample sizes, especially if sample size is less than 50. Shapiro Wilk's test is preferable. And Kolmogorov and Smirnov test with a relatively larger sample size, 50 to 200. If sample size 50 to 200, you can check both of them. And the p-values, if the p-values are less than 0.05, that means if the p-value is significant, the test suggests that the data violates normality assumptions. That means not normally distributed. So to say the data is normally distributed, the p-values should be greater than 0.05. But one drawback is both tests, Kolmogorov-Smirnov, Shapiro Wilk test, they are very sensitive to sample size. When the sample size increases with minimal skewness or kurtosis or deviations, they will become significant. So if the sample size is greater than 200, the researcher should decide checking other tests rather than totally relying on Kolmogorov-Smirnov and Shapiro Wilk tests. Sometimes the same is in our case. If you just base this one, this shows the data is not normally distributed, but from the descriptives we have seen, the data is the mean and median values are very closely related. There is no outliers. So we'll move to other tests. That means graphical presentations. So let's see the graphical presentations for this. Histogram is very important to decide whether the data is normally distributed according to like bell shape, is that bell shape, or whether there is skewness to the right or to the left. Uh, we can draw the bell shape in, let me show you. For example, here in the explore option, we don't have the shape. So let's go to frequencies. Let's bring our variables here. We don't need that, just charts. Histogram, good. Okay, great. Then let's see, this is the bell shape. So ADHD almost smoothly fit the bell shape. Let's see also for anxiety. The same is true also for anxiety. It's almost closely fitting the bell shape. It seems a little bit negatively skewed. That means a little bit. It seems negatively skewed. The details, the values are concentrated a little bit concentrated on the right side, the highest side. The other is self-esteem. This seems perfect. Bell shape, it feels the bell shape still good. The same is true for depression. It fills the bell shape almost nicely. So this is checking histogram. You can check histogram before deciding to follow parametric or non-parametric tests. So one of the graphs is histogram. The other important graph is QQ plot, quantile plot. So in QQ plot, if the data is normally distributed, these data points are the data points. They closely align the line. This is the observed value, and this is the expected normal. So if the dots closely align with the line, that shows the data is almost all normal distributed. Okay, the last graph uh, we check for distribution or for normality distribution or the data distribution is box plot. Box plot is good to detect outliers. Let's discuss about the anatomy of the box plot. The blue box shows the middle 50% of the data in our data set. This the lower border of the box plot shows Q1, quartile 1 or 25th percentile, and the upper line shows Q3, quartile 3 or 75th percentile, and the middle line, this is the middle black line, it is the median or the median value. So the box plot shows the interquartile range Q3 minus Q1. This here is explained by the box plot. When you are reporting the median, especially if the data is not normally distributed and if you use non-parametric tests, you have to report the median with 25th and 75th percentiles, or you have to report also interquartile range. The whisker above the box shows that it ranges from Q3 value to the largest value in the dataset. That's 1.5 times interquartile range above from Q3. And the whisker below Q1 shows that it extends from Q1 to the smallest value in the dataset. That's 1.5 times interquartile range. Data, for example, if there's data that's lower than that range, it will be shown here as an outliers. So in our case, I think in all of the box plots, there is no outliers. But for practical purpose, let's make an outliers and see how does it look like. Okay, for practical purpose, just let's make some values. Let's change and see how it will be displayed in box plot. For example, let's make this 45 and let's make this negative 5 and let's make this 34 and run the Explorer. Great. Here is our box plot. Yeah, as you have seen earlier, there was no outliers, so we haven't seen a box like this as well as star. But now, in two occasions, there is boxes. That means the SPSS assumes these values are outliers, and the one with the star is much far or extreme values in the dataset. So at this stage, before going to further analysis, we have to manage them. These cases, this ID number 1, 2, 3 shows that something is wrong with the dataset. It might be with data entry. So if we have an access to the questionnaire, we have to go back and check the questionnaires. That means data entry. Sometimes it might be by error. For example, a person wants to write 15 and might write 45 by error. That might be corrected by checking the questionnaires or data entry. The other way to correct is if that's not possible, the other solution is completely removing that case from the analysis is another option. And the third option, still some scholars use that. Rather than removing that particular person completely from the analysis, assigning the largest value of the normal data. For example, we have seen that 20 is the largest value for individuals above 20. If you assign 20, that means there will not be extreme cases or outliers, and you can keep that individual. And maybe if the other part of the variables are correctly entered, so still you can keep that individual. The same is true at the lower end of the analysis. So always outlier management. I mentioned three things. One is going back and checking from data entry. That means through the questionnaire, there may be error while entering the data. The second part is completely removing or deleting that case. And the third one is assigning the largest or the smallest value in the data set and keeping these observations. This is all about normality checking. So after checking all, here is my tip. After checking all, you can decide whether to go for parametric or non-parametric tests. These important parts are, for example, we have seen the descriptives. If the descriptives, in the descriptives, the mean, the trimmed mean, and the median, if they are close enough, that's a positive sign to go for parametric tests like t-test, independent sample t-test, paired sample t-test, or ANOVA, regression, correlation, percent correlation, and the like. If there is a huge gap here, for example, the mean and the trim mean and the median values is far away, it might suggest go for non-parametric tests like Mann U Test, Kruskal walls, or Spearman's ANOVA and Spearman's correlation and the like. So one of the things we will check is descriptives. The other is test of normality, the important test to decide for whether to go for parametric tests or non-parametric tests. And the parametric tests here, to go for parametric tests, you will check the Kolmogorov-Smirnov and Shapiro Wilk tests. Shapiro Wilk test is powerful if sample size is small, that means less than 50, and Kolmogorov-Smirnov is good for larger sample sizes. So we'll check the p-values. If the p-values are greater than 0.05, we will go for parametric tests. Otherwise, we will go for non-parametric tests. The other thing that we look is histogram, the important parameter. Histogram will check the shape of the data distribution, how it's distributed. Here we introduced three extreme values, so this shows their effect. So if the distribution is like normal bell-shaped, that's good. We will see the distribution. And from this distribution from the histogram, also we can see skewness, whether the data is skewed or not. Sometimes the data may be negatively skewed. That means most of the observations might be higher or the larger than the mean value, and few extreme low cases that may pull the mean to the lower side, negatively skewed. The other is positively skewed. Negatively skewed, for example, if I can give an example, if in the population, most majority of the people are happy in the service sector, if majority of the people are satisfied with the service, if we have delicate scale asks like that, that will lead to negatively skewed data. And skewness is one of things we have to be careful during deciding analysis. If there is skewed data, so non-parametric tests are advisable. And the other is QQ plot. QQ plot. With QQ plot, we will check how the values are closer to this the black middle line. Initially, we haven't seen like this values. The dots indicate the items or the questions. So this is the first case. It is far away. It's the lower side. It's around -4. So here, look, it's a negative value, and here in the right upper part there is 45 and 34. So it's detached from the other values as well as it's far away from the normal values. So this indicates something extreme values in the data set. So you have to be careful with that. And the last one is box plot. So by evaluating all these, you can decide whether to go for parametric tests